I found this question, which I think is really interesting to think about. Um, I, I haven't solved it yet, but I really want to. And as a challenge to myself, I want to record myself do it. Just to sort of record my thinking process, and maybe upload it because I think it's gonna be very fun to learn how to do this problem. Um, Close my door. Be back in just a second. Okay, but yeah, fun problem. So there's a the center of the disk of radius r, mass m, attached to a spring inside the ring with radius r greater than r. So um, essentially, this little ball here in this hoop connected to like the spring, and this is gonna like go back and forth. And this spring is sort of gonna expand and contract and so on. Um, okay, it's a disc, um, and it can roll without slipping. Okay. Um, Spring can only be attached or compressed along the periphery. Okay. In equilibrium, so okay, this is an equilibrium state. Assuming small displacement. Okay. Um, Fine. We need to find the angular frequency. Okay. So the way I'm gonna do this is using Lagrangian mechanics. Of course, you can attempt to do this using Newtonian physics, but I just think it's an easier thing to do this with Lagrangian mechanics. But the end result, and I'm sure you can again use similar arguments with Newtonian mechanics, but I want to do this with Lagrangian just to show how it's done. Okay, first things first. There's gonna be let's imagine that the ball sort of it rolls and it comes um, let's just say here, right? Um, in that case, it's going to gain this height h at some angle theta. So theta is going to be my sort of, what do you call, the generalized coordinate? Coordinate? Coordinate. Okay. Um, and this is what will describe all my motion. One thing to note is that there's this radial distance r. So the length here, which let's say that this length right here is L, is equal to r minus r. I'll leave it as L for now, and we can see um, what happens with it later, um, right? So yeah, the first things that we worry about when solving things with Lagrangian mechanics is you have your potential, you have your kinetic energy, and you write your Lagrangian as your kinetic energy minus the potential, and you have your Euler Lagrange equations, which are basically, you take the derivative of L um, with respect to like your generalized coordinates time derivative, um, and you set it equal to the thing partially differentiated with q, but you will notice there's a time derivative here, which means really there's a there's a divided by t here, which shifts up. So there's essentially a in the units there's a t here, so we must divide by t. Again, this is not a proof of Lagrange's equation by any means. I just remember this. I just use this to like recall the form. the general form is like one partial and a full-time derivative setting up equal to another partial, but I just, don't remember whether the dt is here or here. And one way I can convince myself it's here is this. Again, the way you come about Lagrange's equation. I mean, there's a rich history and all that, but the way you do that on your own is using an integral that is of Euler-Lagrange type, and then you do some continuum mechanics and calculus of variations, not continuum mechanics, calculus of variations, and um, using some math, come about. From what I remember, you have this integral, and you have like something um, dx being equal to 0 or something, and you realize this is going to be 0, and yeah, and that something happens to be like this minus that or the other way around. But yeah, whatever. So that's our general idea. Um, in our case, in our case, theta is our generalized coordinate, so theta dot, or the angular velocity is going to be our q dot. So what is the potential? Well, there's going to be two potentials. One related to this spring, right? And the other related to the force of gravity. Okay, so let's see. The one related to the spring, again, the spring's potential energy is like half kx squared. X in our case will be whatever this length here is. Let's call this like S. You would know that by definition theta is defined to be S over L. So from here, S equals theta L. By the way, this is why, for 2 pi radians, there is 2 pi r distance, the circumference traveled for a radius of r. That's how you define theta. So S is theta L squared, theta L, so this will be theta L squared. So that's the spring part. You then have the gravity part. Now, the potential energy due to gravity is just mgh. Now, how much is the distance h? Well, if you look at this triangle, you look at this triangle, there's this height h, there's an angle theta, this is L. This of course is L cosine theta. This is, in case you're wondering, L sine theta. This entire length is L, so h is the entire length, L minus this length, L cosine theta, which is just L times 1 minus cosine theta. Okay, so that's my h, 1 minus L times 1 minus cosine theta. I don't see any thetas here, and well, I've done problems like this in mechanics, but usually you want to look at this small displacement and realize that you're going to use a small angle approximation. Now, cosine theta is about 1, but the second Taylor expansion term is theta squared by 2. I mean, the others go like theta to the 4 by 4 factorial and so on, but really you can neglect these and only look at the first two terms. And if you notice then that h times L, h being equal to L times 1 minus cosine theta will then about be L times 1 minus theta squared over 2. and that will just be L theta squared by 2. Okay, so that will be L theta squared by 2. Okay, now the kinetic energy. So this was potential. This is the kinetic part. Let me just, make sure that we don't have any other part. Spring, the gravity, and yeah. Now the kinetic part, um, well, kinetic energy is half. Okay, well, I should talk about another thing first. In mechanics, whenever you have sort of a motion of an object, um, you know, in space, um, and the thing is, also rotating and stuff. Um, I mean, it, it's a theorem that you can prove, but you can always decompose the motion of an object um, as motion of the center of mass plus motion of body around center of mass. So in essence, if there's a ball that is rotating here, you can first talk about sort of the ball as like a non-rotating ball, or rather just a point, the center of mass, translating through space. And then you can talk about the ball as if it's stationary so you can talk about it in the center of mass frame, and you can talk about the rotation um, happening at like some, I don't know, angular velocity. Um, yeah. Okay, so that's what we're gonna do. So we're gonna have the kinetic energy broken down as like half mv squared for the center of mass, and then about the center of mass we're gonna decompose it as like the rotational kinetic energy, half I omega squared, um, and well, there's a there's a neat thing happening here actually. I read it somewhere. Um, where is it? No slipping, no slipping. You have to be careful with that, because if there's slipping, you can imagine that, you know, um, your thing is spinning on its own, but it's not moving, right? So is this omega? My question is this omega the same as theta dot? And it turns out that if you talk about no slipping, um, the thing about no slipping means that when your thing is moving and you have your ground, um, I think from what I remember, no slipping condition means that there is no relative velocity between your point at the bottom, so the point at the bottom, and the ground point. I think this is what no slipping means. And if we consider that we are moving at some angular velocity theta dot, then the velocity of the let's say this is bottom B, this is the point E of the ground, then the velocity at the bottom is what? It's um, again, um, let's see. If this is R, if this is R, then again, theta equals sort of S over R. So theta dot equals S dot over R, where S dot is just V at the bottom. So in the center of mass frame, V at the bottom will be, it will be R theta dot. And we know here, that again we considered this s to be um, that. Okay, okay. Wow, this is interesting. Okay. We think about it for a second. Is this going to be the same omega? Is this going to be the same omega? Let's see. So what's the ground velocity? What's the ground velocity? So it's traversing, what's its velocity here? It's theta dot equals s dot over L. Okay. So that's the velocity it is going this way. So velocity it's going this way. Very interesting. Okay. Hmm. Yeah, I think it makes sense. So with the no slip condition, I think, or yeah, I think it is fair to say that the theta here, but okay, this is interesting. This is interesting. Maybe there's two different thetas involved. Okay, so maybe there's this ball, and there's this theta, there's this theta, and then there's the ball here. And if we consider a point here, maybe there's another theta here, right? Maybe there's another theta here. And the question is, which of how are these thetas related? Now, I think for this ball alone, for this ball alone, for this ball alone, um, if you look at the place here, if you look at the thing here, um, okay, I think I got it. The point here, the center of mass, is moving at a velocity v. We know that in time t equals 2 pi by theta dot, where theta is the theta for this small ball. Let's call it theta small. And this time, the distance, which is the velocity r theta dot over time t equals 2 pi r. But t is 2 pi over theta dot. Oh, wait. Yeah, 2 pi by omega velocity over time. Oh, no. What am I doing? What am I doing? Velocity equals distance upon time. So distance is velocity times time. So r theta dot equals or times 2 pi by theta dot. Okay, 2 pi r, correct. Okay, and this must have had spin 2 pi r. Therefore, these omegas are clearly the same. Yeah, I think this makes sense. So the transversal the translational velocity here is the same. Okay, so it's clear that the condition here is this is true. Um, this is true um, with respect to the center of mass and with respect to P, just because of this translational game that we played here. Okay, again, you have to be careful with this. And I forget what the thing here was, but I'm sure you can play around with this and I guess be more rigorous with this. But yeah, okay, coming back. Now we have two different thetas. Let's call this theta dot and this one just theta. How are theta and theta dot related? My guess is that theta dot is the same as theta dot dot. So the big theta has the same angular velocity as this small theta. And I think the idea is that if I go around and have, say, okay, so I have this length L, I have this length L, and the thing traverses a distance S equals, well, theta equals S over L, so S equals L theta, okay, at the same time, um, by this argument, keeping this in mind, once we get a result from the no slip condition, the velocity that it's moving with is or yeah, the distance that it traverses rather is r theta dot um or okay, yeah, what we can do is the following. How many circumferences go in this length? Well, that's 2 pi r is the distance of one circumference, so we divide L theta divided by this. So this is the number of circumferences that go into that. And S dot would be this times the circumference. Okay, this is interesting. I have to bring in a time parameter. Okay, let's assume that we're moving at velocity theta dot, angular velocity theta dot. In time t, we traverse theta dot times L times t distance. Okay. In the same time t, assuming we had an angular velocity theta dot dot for this small guy, it will traverse a distance equal to its velocity r theta dot it will traverse the distance equal to r theta dot, right? That was a velocity. Where does this length thing come from? Oh yeah, velocity there. Theta dot t. That's okay. Interesting. From here, since these must be equal, so theta dot equals theta dot times L over R. Very interesting. Okay. Okay. That's something. Anyways, it doesn't change that. Doesn't change the kinetic energy. Or not this potential energy, not the gravitational energy. It will change the rotational energy, right? The kinetic energy will still be half m times theta dot L, right? So the kinetic energy will be like related to this lever arm, but the rotational energy will be related to this small lever arm, right? So it will be I half I omega squared, where omega will be theta dot squared, but we know that theta dot is, or theta dot is theta dot times L over R. Should have come up with a better name, but so this will be theta dot times L over R squared. Now, as for the moment of inertia of a disk, well, moment of inertia is the integral of dm r squared. I would break it down as like sort of tiny tiny rings of thickness dr. So the mass dm would be some density sigma times the area 2 pi r dr, sigma 2 pi r dr times r squared from 0 to r, and that is sigma is the mass m over pi r squared times 2 pi is a constant, and the integral of r squared from 0 to r is r to the r cubed, sorry, from 0 to r is r to the 4 divided by 4, and that happens to be mr squared divided by 2. It's the moment of inertia of a disk. It's half m r of the disk squared divided by 2, and that's it. That's all there is to Lagrangian mechanics, as far as physics goes. now all that is left is sort of computation. Um, One thing that I would like to do is sort of simplify these first. So that's k, kl squared um, theta squared over 2 plus mgl theta squared over 2. The kinetic part is ml oops, squared theta dot um, theta dot squared over 2 plus um, plus m r squared L squared over R squared theta dot over squared over 2. There's another 2 here. Notice the R squares cancel. Interesting. So it's all now in terms of L. I'm guessing there's an L squared missing. Potential energy is mgh. No, yeah, this is fine. Half kx squared mgh. Yeah, seems fine. Seems fine. Yeah. Now we write whatever this is. Do that. Now we just differentiate. So what is the derivative of the thing with respect to q dot? It's this guy. It's gonna be ml squared theta dot. The 2 comes down, cancels with that 2. And then you differentiate with respect to time. And so that becomes that. You will notice this is just your angular frequency alpha plus the differential of this guy. Again, you will notice this just becomes theta double dot. So this will become m over 2 L squared theta double dot. That is equal to um, that is equal to um, the potential term. Since there's a minus in L, you'll all have a minus here, and we can differentiate with respect to Q, which is our theta. Again, this theta will just be 2 theta, but it'll cancel with the 2, so this will become KL theta plus mg, or KL squared theta plus mgl theta. Very interesting. Oof. Okay. Now, now we realize this is a differential equation in theta dot, theta double dot, and theta. So just the differential equation in theta. Collect like terms times the 3/2 of these is equal to minus um or yeah is equal to minus KL squared plus mgl theta. You bring this down here. Notice this is your this is your um, this is your um, omega squared. This is yet another omega, which is the angular frequency of the motion. Um, wait, let's call this lambda. Yeah. Okay. Um, or let's call this omega itself. But remember, this is not your um. This is not the omega related to this theta. This is yet another omega. Um, yeah. So the solution to this ODE is just, or this is omega squared actually, is sort of a sine, I mean, in general, it's a sine omega t plus phi, but your starting point is 0, so you can not do that. But yeah, in essence, this basically is the answer. Um, I mean, I don't know if this matches any of it, but let's see if we can simplify things further. Let's see. So omega squared equals kl squared plus mgl divided by 3 by 2 ml squared. So that is just, let's divide through by L squared, and I mean, let's just separate these out. 2 by 3 K over M plus 2 by 3, let's see, G over L. Yeah, that's what I hope it to be. Yeah, and remember, L was R minus R. So my final answer, divided in red, is omega being the square root, because it says omega squared, omega being the square root of 2 by 3 times k over r minus r plus g, or whoops, g over plus k over m. Does that match any of us? Oh wait, it does match the first one. It does match the first one. Time for the reveal. Is that the answer? It is. Okay. I still got my thing, but with Lagrangian mechanics. It's wonderful. But yeah, I hope you learned things for this video. So Lagrangian mechanics, it's very beautiful. I mean, I really encourage you to learn about Lagrangian mechanics. It's beautiful history, and there's all the work that you do is getting to this Euler-Lagrange equation, which you do with calculus and variations. But the idea comes down to this quantity, the Lagrangian, which for classical physics is just the kinetic energy minus the potential energy. Kinetic energy is just half mv squared plus whatever your rotational kinetic energy is. Potential energy was kind of straightforward. The only caveat for us was, and I actually didn't realize it, but at the end this was something very important, I guess, since otherwise the answer would have been wrong. But at the end, this would not have been our square dependence. This would have just been an L square dependence, because this R cancels. And the reason it cancels is because this angular frequency of this small guy is related to this theta with like a scaling factor L over R, because of how when you traverse this distance theta, a little theta naught I guess it's a better terminology, for this little guy is different. So in essence, in time t, if you traverse a distance theta l t, in the big frame, you traverse a distance r theta naught dot t in the little frame, so there's just L over R. Um, but yeah, at the end, you just get your potential, get your kinetic energy, and use Euler-Lagrange equation, differentiate. Notice this is just your um, your angular acceleration. This is sort of your angular acceleration, but divided by 2, which comes from sort of that moment of inertia having that divided by 2 part. And if you realize physically, again, the beauty of Lagrangian mechanics is that, it works when your physical realizations beyond human intuition, or you haven't yet developed them for certain field of physics, like quantum mechanics, GR, whatever. But physically, this represents sort of your angular acceleration term. So I alpha equals um, but yeah, this is exactly I alpha, and this is sort of, I don't know why it's squared, but some kind of I alpha equals the torque. So the torque here being, let's see, mg being your force, and minus kl being your force there, and L theta being sort of your lever arm. So that's force times your lever arm, and that becomes your net torque. So that's how you could have done this with Newtonian mechanics, which again, I'm not saying this is a much better thing, but this is a more elegant thing, especially when things get more complicated. And this is more like sort of brute force way, which works all the time, which I don't know, it's just really interesting. But yeah, I think now that I think about it, it may have been more practical to solve this with Newtonian mechanics, but regardless, I think you can already appreciate how at the end Lagrangian mechanics, we didn't think about a lot of kinetics. We just thought, okay, there's a kinetic energy with velocity v, there's potential energy, rotational kinetic energy. That's it. That's all we did. And then we just did some calculus and realized that what we get in the end is like an ODE in theta, and that's a form like it's a form theta double dot equals minus omega squared theta. Again, this omega, the angular frequency of the motion, not related. I mean, it is related, but it's not the omega that you get by differentiating theta. So this is not equal to theta dot, right? But yeah, its solution happens to be sine omega t minus plus phi minus phi, doesn't matter, with some scaling factor. I mean, in general, it's really like a sum of all exponential terms. So this plus with an I here because of the minus p e to the negative I omega t. But yeah, simplify it down. At the end, you get this omega. Beautiful. But yeah, I solved the JEE advanced problems after like a long while. And well, in the actual exam, um, Really, you don't have to spend like half an hour on one problem. Really, it's like 2 minutes, 3 minutes, 5 minutes. So really, you would have noticed like, oh, there's like this torque term, this torque term, this torque term, this torque term, and these are like sort of the i's, and alpha isn't. Yeah, that's what you would have done. Again, the point here was not to solve this problem, but to learn things in physics through this problem. And I hope you did that. And I hope you had fun. Hope you learned something new. And well, still need uh, still need some definitions here. I think a little loose on this. Um, but yeah, you can do that. Um, and yeah, see ya.